In Chapter 1, we learned different ways to classify matter. One way was by distinguishing between an element or a compound, both of which were pure substances. If we break down a compound even further, we can either describe it as being molecular or ionic. Molecular compounds are also known as molecules. A molecule is a neutral particle composed of two or more atoms combined in a fixed ratio. Molecules consist of discrete particles. If you think of anything that you could draw a Lewis structure for, or a compound that would be able to be built by a model, those are going to be your molecules. Methane, or natural gas, is CH4. This would represent a molecule. Chloroform is CHCl3. There are also a few elements that exist naturally as diatomic molecules. If it's an element, we wouldn't say that it's a compound, but they can still exist as molecules because there's two atoms combined together. Water molecule, or H2O, would be another example of a molecular compound. Molecular compounds are electrically neutral particles. They consist of two or more atoms combined together, and the bonds between atoms are formed from the sharing of electrons, sharing being the key word. And you'll notice if you look at all the types of atoms in molecules, they are all nonmetals. The sharing of electrons always occurs between two or more nonmetals. In ammonia, we have nitrogen bonded to 3 hydrogens in this ball and stick figure. So NH3 would be considered a molecule. Ethanol, or drinking alcohol, consists of carbon and hydrogen bonds on the left-hand side, and then an alcohol functional group, or an OH bond, on the right side. But it consists entirely of carbon, hydrogen, and oxygen, which are all nonmetals. That's the key for identifying a molecule or a molecular compound, is looking and seeing if it's all nonmetals combined together. On the other hand, ionic compounds are formed from the reaction between metals with nonmetals. And they do not share electrons like molecules do. Ionic compounds are formed from the transfer of electrons from a metal to a nonmetal. Ionic compounds are made up of ions. Ions are charged particles. There's a cation, which is positively charged, and an anion, which is negatively charged. If we look at the formation of the ionic compound sodium chloride, which is just ordinary table salt, we can see that it's made up of sodium metal and chlorine gas. Remember that chlorine occurs naturally as a diatomic molecule, which means that there will be two chlorine atoms bonded together naturally. While sodium is a metal and chlorine is a gas, sodium chloride as a compound does not exhibit any of the properties of the things that make it up. When sodium loses an electron, it becomes a sodium ion. Metals tend to lose electrons to become cations. Cations will have a positive charge, and they're represented by the blue plus signs. On the other hand, chlorine is a nonmetal which likes to gain electrons. The chlorine will gain 1 electron to become an anion, which is a negatively charged ion. Sodium chloride is really just a bunch of repeating positive and negative charges over and over again. When we have 1 sodium ion that has a positive charge and 1 chloride anion that has a negative charge right next to each other, this is called a formula unit. It represents the smallest, simplest unit of an ionic compound, which is not the same as a molecule. So to compare molecules or molecular compounds against ionic compounds, molecules are neutral particles that are made up of two or more nonmetals together. So the elements will always be from the upper right-hand corner of the periodic table. The bonds between a molecule are formed by sharing electrons. You can think of a molecule as something you could draw a Lewis structure for, such as water, H2O. Ionic compounds are made up of ions. So there's going to be a bunch of positive and negative interactions that hold the substance together. They're composed of a metal with a nonmetal, and the bonds are formed from the transfer of electrons from the metal to the nonmetal, rather than sharing electrons as we saw in molecules. Predict whether the following compounds are ionic or molecular. Ki, the compound used as a source of iodine in table salt. We have potassium, which is a metal, with iodine, which is a nonmetal. So this is going to be an ionic compound. H2O2, hydrogen peroxide. We have two or more nonmetals together. Reminder, hydrogen is in group 1A, but it is a nonmetal. So this is going to be a molecule. CHCl3, which is chloroform, is a whole bunch of nonmetals. So this is also going to be a molecule. And lithium carbonate. Lithium is a metal, and carbonate is one of our polyatomic ions. And since it's an ion, we have a positively charged cation, which is our metal, with a negatively charged polyatomic ion. This is going to be an ionic compound. When we look at the periodic table, we can predict what charge elements that are representative elements will form. So our representative elements are the first two columns of the periodic table and the last six columns. Group 1A, which is the alkali metals, will always form a +1 charge when it becomes an ion. Group 2A, which is the alkaline earth metals, will always form a +2 charge when it becomes an ion. Group 3A elements that are metals, such as aluminum and gallium, will always form a +3 charge when they become an ion. If you notice, we're skipping over group 4A because those elements tend not to form ionic bonds. They tend to be involved in molecular bonding, and so we don't need to know what charge they form. Now looking at group 5A, we have nitrogen and phosphorus, which are nonmetals. The nonmetals like to gain electrons rather than lose electrons. Elements in group 5A will always gain 3 electrons to develop a -3 charge. Nonmetals in group 6A will gain 2 electrons to develop a -2 charge. And the nonmetals in group 7A, the halogens, will pick up 1 electron and always have a -1 charge when they become an ion. We can also ignore group 8A, the noble gases, because they do not bond with pretty much anyone. They already have a complete octet of electrons and are stable. So later in this class, we'll learn why these different groups form the charges they do, and it has to do with their number of electrons and their stability, we'll see. But for now, all we need to know is what charge they form based upon what group they're in on the periodic table. So metals, we know, form cations, meaning they lose electrons, and nonmetals form anions, meaning they gain electrons. And don't worry too much about the listed transition metals. There are a few transition metals that always form the same charge, such as silver always forms a +1 ion, zinc always forms a +2 ion. Just as we predicted the number of protons, electrons, and neutrons for specific isotopes, we can also predict the number of protons and electrons for ions. So anions will be negatively charged, which means that they gained or picked up some extra electrons. Cations are positively charged, which means that they lost electrons. Electrons have a negative charge, so if you gain more, you will develop a negative charge, and if you give up some, you will have a positive charge. So for example, if we look at this representation of a sodium atom, sodium's atomic number from the periodic table is 11. So that means that it has 11 protons in its nucleus. In a neutral sodium atom, the number of protons is exactly equal to the number of electrons. When sodium becomes an ion, it gives up its one valence electron. Sodium is a group 1A metal, and we just saw in the previous slide that any metal in group 1A forms a +1 charge. So that means sodium will lose one of its electrons to form a +1 charge. In the ion, it still has 11 protons in its nucleus, but now it only has 10 electrons surrounding it because it lost one. We can always count the number of electrons that a specific ion will form if it is a representative element. How many protons and electrons are in the following ions? Magnesium 2+. If we look at the periodic table, the atomic number for magnesium is 12. So Z equals 12. That tells us that the number of protons in a magnesium atom is equal to 12. In a neutral atom, the number of electrons would also be equal to 12. But since we formed a +2 ion, that means that our magnesium atom must have lost 2 electrons. Therefore, in this ion, the number of electrons is going to be 10. Nitride ion, which is N3-, the atomic number of nitrogen is 7, according to the periodic table. That tells us that a nitrogen atom has 7 protons, and the number of electrons normally would be 7 if it was a neutral atom. But our 3- charge tells us that it gained 3 extra electrons. So our total number of electrons must be 7 plus 3, or 10 electrons total. So a nitrogen that became an ion and gained 3 electrons will have 7 protons in its nucleus and 10 electrons surrounding it in the electron cloud. Next, we're going to switch gears and focus on chemical nomenclature, or in other words, naming. Naming is a very systematic process, and there are a lot of rules to learn in order to name different types of chemical compounds. With naming, the best thing you can do is practice, practice, practice until you get the rules down. The different categories we'll learn how to name: ionic compounds, which we learned are made up of a metal and a nonmetal. There are binary ionic compounds, which contain 2 different kinds of elements. We can have binary ionic compounds that are made up of our representative main group elements, or binary ionic compounds that have metals that are transition metals. We'll look at ionic hydrates. Those are compounds that contain water within their structure. And then ionic compounds that contain polyatomic ions. There's a list of polyatomic ions on Blackboard that you should be memorizing. You will not be given that on a quiz or exam, but you will need to know the polyatomic ions for the rest of the semester. First, when we look at naming, and later when we write chemical reactions and do Lewis structures and molecular geometries. You need to know the name of the ion, the charge on the ion, and the formula for the ion. I suggest making note cards. The second main category will be molecular compounds. We know that molecular compounds are made up of 2 or more nonmetals, and in this class we'll just focus on binary molecular compounds. So binary refers to two different elements together. Lastly, we'll learn how to name acids. There are binary acids, which contain hydrogen with a different nonmetal, and then oxyacids, which are acids that are derived from the polyatomic ions that you'll learn. So let's get started. We will start with binary ionic compounds that are formed from our main group or our representative elements. This is a good place to start because we can predict what charge an element will form based upon its group number. Ionic compounds have to involve ions, so cations and anions. We can use cations that are formed from our metals and anions that are formed from our nonmetals to practice writing names and taking names and writing formulas. When writing a name from a chemical formula for a binary ionic compound, the pattern is that we first write the metal name, which will come from the left-hand side of the periodic table, followed by the nonmetal name, only we change the ending or the suffix of the nonmetal to "ide", IDE. The metal will represent our cation, or positive ion. The nonmetal will represent our anion, which is our negative ion. The number of ions does not need to be specified in the name. This is because we are only looking at main group elements, and we know they will always form the exact same charge. So let's look at some examples. We have the formula NaCl. Na is a metal, and that will be sodium. Chlorine is a nonmetal, only we will change the ending of chlorine to IDE, or ide. So the name of the compound is sodium chloride. MgO, the metal, is listed first, and this is magnesium. Oxygen is the nonmetal, and we change that to oxide. LiF, Li is the element lithium. F is the nonmetal fluorine, and that will be changed to fluoride. Lithium fluoride would be the name. CaBr2. Now we don't need to do anything with this number 2 here. That's the appropriate chemical formula, but when we're converting a formula to a name, we simply name the metal, which is calcium, and then we name the nonmetal, which is bromine, only we change that to bromide. Same with Kn3. We don't have to do anything with the 3. The metal K is potassium. Following our trend, we list the metal first, followed by the nonmetal. Nitrogen becomes nitride. Later, when we work backwards from a name to writing a formula, you'll see why the 2 and the 3 are listed. They're important, but not when writing the name. Now we're going to work backwards, writing a chemical formula from a name. And we're still just looking at main group or representative elements and doing binary ionic compounds. First and foremost, the formulas that we write must always be neutral. That means that the sum of the positive and negative charges must add to 0. This will determine the number of subscripts that we need for a given element. The cation is listed first, the anion is listed second, and the subscripts that we write should always be the smallest set of whole numbers possible. It is possible that you could have to simplify at the end. And never, 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 never leave any charges in your final formula. It's okay if you write some charges on your ions while you are figuring out what the formula is, but do not leave them in the final formula that is your answer. Otherwise, it will be wrong. So let's try some examples. It would probably be useful to keep a periodic table by your side while you're practicing.
We want to write the formula for sodium bromide. The chemical symbol for sodium is Na, and sodium is a group 1A metal, which means it forms a +1 charge. Bromide comes from bromine, which is a group 7A nonmetal, which means it forms a -1 charge. I'm only writing the charges for now so we can see how to write a neutral formula. I have a +1 charge and a -1 charge. Together those add to 0, or neutral. So my formula for sodium bromide is simply NaBr. Barium sulfide. Barium is a group 2A metal, and it forms a +2 charge. Sulfide comes from sulfur, and that is a group 6A nonmetal, which will always form a -2 charge. So we have a cation with a +2 charge and an anion with a -2 charge. If we have one barium and one sulfur, the charges will cancel each other out and give us a neutral compound. So our formula for barium sulfide is BaS. Lithium selenide. Lithium is a group 1A metal. It forms a +1 charge. Selenide comes from selenium, which is Se. It's a group 6A nonmetal, and it will always form a -2 charge. So now if we were to put those together, one lithium with one selenium ion, the charges would not cancel. We only have a +1 and a -2. We'd be left over with a -1 charge. So a trick you can do is take the numbers from the charges and cross them, putting a 2 after lithium, and then the plus represents a 1 after selenium. So our neutral formula would be Li2Se. If we think about the charges then, we have 2 positive charges because we have 2 lithiums, and we have 1 -2 charge because we have 1 selenium. Overall, our charges add to 0, so our formula is neutral, which is what we want. Magnesium chloride. Magnesium is Mg. It's a group 2A metal. It forms a +2 charge. Chlorine is a group 7A nonmetal. It's a halogen. In an ion, it forms a -1 charge. We can apply the same principle we just talked about with our last example. Right now, our charges won't cancel if we just have one of each atom. But if we cross the charges as subscripts, so the 2 will go after the chlorine, 1 would go after the magnesium. And we never have to write one, it's just implied. So our neutral formula would be MgCl2. Strontium phosphide. Strontium is atomic number 38. It's a group 2A metal, so it forms a +2 charge. Phosphide comes from phosphorus, which is in group 5A. All the elements in group 5A will form a -3 charge because it's a nonmetal. So we want to write a neutral formula. So we're going to take our 2 and put it after the phosphorus, and we're going to take our 3 and write it after strontium. Our neutral formula is Sr subscript 3, P subscript 2. Remember, you always want to write a neutral formula and not leave any charges in your final answer. You also need to know, based upon what group number your element is in, what charge it will form. When writing formulas or coming up with names for binary ionic compounds that contain transition metals, we're going to follow most of the rules we just learned previously. But now we have to take something else into account. Transition metals do not just form one ion. Many of them form multiple ions, such as iron forms a +2 charge and a +3 charge. Copper forms a +1 charge and a +2 charge. There are also a few that are in group 4A which fall outside of our transition metal block, such as tin, Sn and lead, Pb. They happen to also form multiple ions, so we treat them like transition metals. We have to indicate the charge of our transition metal in our name. We cannot predict what charge a transition metal will form like we could for our representative elements. When we are writing a name from a formula and it contains a transition metal, our pattern will be we still list the metal first, but now in parentheses, we also have to indicate the charge of the transition metal. We still second write the nonmetal and change the suffix to "ide." So for example, iron we said formed two charges. Iron 2 plus is named the iron 2 ion with 2 written in Roman numerals in the parentheses. Fe3 plus represents the iron 3 ion. 3 is written in Roman numerals in parentheses. We can do this for any ion that forms multiple charges. The method that we'll use in order to figure out the unknown charge on a transition metal is to start with the anion first. This is a surefire way to determine the charge on our transition metal since it can't be predicted. With binary ionic compounds that contain transition metals, it's a little easier to start with writing the names first. So we will begin here. CuBr. We know that bromine is a group 7A nonmetal, and it's also a representative element, so we can predict that bromine is always going to form a -1 charge. If we know already that CuBr is a neutral formula, the charge on copper in this compound must be +1 because there's not multiples of either of them. There's only one listed. So our name for this compound is going to be copper 1, we listed in parentheses, and then bromine becomes bromide. For the next one, the chemical formula is CuBr2. So if we start with the anion, which is the bromine, we know it has a -1 charge. Our copper has to cancel that out, that -1 charge. But how many bromines do we have present? We have 2 bromines according to the chemical formula. So overall right now, we've got a -1 charge on one of the bromines. We have another -1 charge on the other bromine. In order for that to be a neutral formula as written, the charge on the copper in this compound must be +2. So our copper in CuBr2 has to be a copper 2 ion. So when we name this, we're going to indicate that copper 2 bromide. Iron is another good example of a transition metal. FeO, we're going to start with the anion, which is oxygen. Oxygen is a group 6A nonmetal, always forms a -2 charge. We can predict that. And since there's only one iron for every one oxygen, remember there's unwritten subscripts of 1 after each of those, that means our iron ion must have a charge of +2. So when we name this, this is going to be iron 2 oxide. With Fe2O3, we'll still start with the oxygen. Oxygen has a -2 charge, and we're trying to work backwards to figure out what the charge on our iron atom is. So now, looking at our chemical formula, there's 3 oxygen atoms for every 2 iron atoms. That means that we have 3 -2 charges. And if we are restricted to having 2 iron atoms, what charge must each of those be so that the formula is neutral? We know they're going to be positive because it's a metal. Each iron must be a +3 charge. That gives us a neutral atom. So that, working backwards from our anion, allowed us to figure out the charge on our cation. The name of this compound is iron 3 oxide. SnO2 is tin and oxygen. So just as we saw before, oxygen is still going to be a -2. And we don't know right away what the charge on our tin atom is. If we start, we know we've got 2 oxygen atoms for every 1 tin. So we're going to have -2, -2. We only got 1 tin atom. So to make this neutral, the charge on our tin must be +4. So our chemical formula converted into a name will be tin 4 oxide. This can be a little tricky at first, so you need to practice. Going backwards should seem significantly easier now. When writing a formula from a name, we're going to know exactly what the charge on the metal is because we have to be told that in the formula. Our formulas still must always be neutral, just like they were before. Positive and negative charges add to 0. We still list the cation first, the anion second. Our subscripts are still going to be the smallest set of whole numbers, and no charges in our final formulas. All right, so let's try some examples. Iron 2 chloride. So we're told we have iron 2, Fe2+. Chlorine is a group 7A nonmetal, and we can predict the charge. It'll be -1. So if we go back to what we learned before, the trick for writing a neutral formula, crossing the charges as subscripts. The neutral formula will be FeCl2. Cobalt 3 sulfide. Cobalt, we're told, is a +3 ion. Sulfide comes from sulfur, group 6A nonmetal, always forms a -2 charge. If we take our subscripts and we cross them, we put a 3 after the sulfur, we put the 2 after the cobalt, that'll give us our neutral formula. CO2S3. Copper 2 phosphide. Copper 2+, we're told, and phosphide comes from phosphorus, which is a group 5A nonmetal. It's going to have a -3 charge. So we take our 2 and we list it after the phosphorus. We take our 3 and we list it after the copper. This crisscross will give us our neutral formula, Cu3P2. Silver 1 oxide. Silver is Ag, and it's silver 1, so it has a +1 charge. Oxygen is a group 6A nonmetal, has a -2 charge. We're going to list the 1 after the oxygen, but we don't have to write that explicitly. We're going to list the 2 after the silver. This will be Ag2O. And lastly, tin 4 fluoride. Tin is Sn. We know it has a 4+ charge. Fluorine has a -1 charge. So when we cross those, we're going to have a 1 after the tin. We're going to have a 4 after the fluorine. And our neutral formula will be SnF4. Next, we're going to name ionic compounds that contain polyatomic ions. If you do not know your polyatomic ions yet, I suggest printing off the handout on Blackboard and keeping it next to you while we practice. When we're writing a name from a formula, there's a couple patterns we can follow. If we have main group metals, the trend will be naming the metal, followed by the top polyatomic anion. If we have transition metals, we list the metal, followed by the charge in parentheses, and then the polyatomic anion after that. We do not change the ending or the suffix of the polyatomic ion to "ide." So that's a new change. We don't have to change it. We just name it exactly as it is. And since most of the polyatomic ions are anions specifically, that means they're going to come second in our naming. There's only one polyatomic cation on your list, which is the ammonium ion, or NH4+. We're given the formula here and we're asked to supply the name, LiNO3. The first thing you want to recognize is that this formula contains a polyatomic ion. This NO3 group comes together as a unit, which is what our polyatomic ions are. So first we name the metal. The metal is lithium. And next we name the polyatomic anion, and we don't change the suffix. NO3 is nitrate. FeCO3. Fe is iron, but this is going to be a transition metal, so we need to figure out the charge this time. CO3. CO3 is one of our polyatomic ions. The name of it is carbonate, and it has a charge of -2. If FeCO3 is a neutral formula, the charge on our iron ion must be +2. So this is going to be iron 2, and then we name the polyatomic ion carbonate. NaOH. Na is a metal, that's sodium. We know the charge on that, that's a +1. Hydroxide is the name of this polyatomic ion. So the name of this is sodium hydroxide. K2SO4. The metal K is potassium. And SO4 is a whole unit together, and that's called sulfate. Cu, parenthesis, ClO, close parenthesis, and then notice we have a 2 on the outside of our polyatomic ion. So the copper is our metal, and it's a transition metal. We're going to have to figure out that charge. ClO, that's one of our polyatomic ions. That's called hypochlorite. In order to figure out the charge on our copper, we have to know the charge on a hypochlorite ion. Each ClO unit has a -1 charge. And according to the chemical formula, we have 2 of them. So the total charge of our chlorates is -2. That must mean that our copper, which remember we have to write a neutral formula, must be +2. So we just solved backwards for what the charge on our copper was. In order for everything to be neutral, it has to be a +2. And last one, NH4CN. This is an example with 2 polyatomic ions. We have our NH4 polyatomic ion. That's called ammonium. It's the only polyatomic cation. And then we have CN, which is another polyatomic anion. This is called cyanide. Notice I didn't change the ending to IDE. Cyanide is the name of the polyatomic ion, just as hydroxide also ends in IDE. I didn't change that. It is just the name of it. You need to practice with your polyatomic ions until you feel very comfortable with them. Next, we're going to write a formula from our name, And all of our compounds are going to contain polyatomic ions. Our formulas still have to be neutral. We'll still list the cation portion followed by the anion portion, and we will not be leaving charges in any of our formulas. So this time we're given the name and we're supplying the chemical formula. Sodium acetate. So we want to work this out. Sodium is a +1 metal. Acetate is a polyatomic ion, and it is C2H3O2 minus. So notice our metal has a +1 charge, our polyatomic anion has a -1 charge, so the charges will cancel each other out. When we write the neutral formula, it'll be NaC2H3O2. Calcium bicarbonate, or another name for bicarbonate is hydrogen carbonate. Calcium is a +2 ion. Bicarbonate, or hydrogen carbonate, that polyatomic ion is HCO3, and it has a -1 charge. So if we're going to write a neutral formula, we have to take our 2 and list it after our bicarbonate ion, and we take our 1 and we would list it after our calcium ion. But whenever we have multiples of our polyatomic ions, we have to indicate that it's a multiple of the whole unit. So we have to put parentheses around it. So our formula will be Ca parenthesis HCO3 close parenthesis, and now we're going to put a 2 on the outside of the whole thing. So that means there's 2 bicarbonate units total. Aluminum permanganate. Aluminum is a group 3 metal, and it forms a +3 charge. Permanganate is a polyatomic ion, MnO4, with a -1 charge. So when we crisscross, we're going to put our 3 after the permanganate, and the 1 will go after the aluminum. So our formula will be Al, and we're going to put parentheses around our polyatomic ion, MnO4, close parentheses, 3. Ammonium phosphate. Ammonium is NH4+. Phosphate is PO4 3-. So here's an example where we have 2 polyatomic ions together. The 1 from the ammonium will go after the phosphate. The 3 from the phosphate will go after the ammonium. When we crisscross them, we're going to have to put parentheses around our ammonium ion to show that we have 3 NH4 units, followed by PO4. So that would be our final formula. Magnesium chlorate. Magnesium forms a +2 charge. Chlorate is a polyatomic ion, ClO3-. When we do our cross, 2 after the chlorate, and 1 after the magnesium. This would be MgClO3, but the ClO3 has to be in parentheses with a 2 on the outside. Ionic hydrates are compounds that contain water molecules as part of their crystal structures. So these are still ionic compounds or salts, but now there's water integrated within its molecular structure. We can never predict the number of water molecules that a specific ionic salt will have surrounding it, but we can name them. So this blue crystal is representing hydrated copper 2 sulfate, or copper 2 sulfate with water in its structure. In order to name an ionic hydrate, we name the ionic salt following the rules that we just learned. There's a dot that goes in the middle, and then we have to use Greek prefixes to indicate the number of water molecules that are in the structure. We'll also use the Greek prefixes later when we name molecules. So when we're writing a name from a formula for ionic hydrates, the pattern that we'll follow is we name the metal, followed by the nonmetal and change it to "ide." If we have any transition metals or polyatomic ions, we also name those as we learned before as well. We include that dot, and then we use the correct Greek prefix followed by the suffix hydrate. The Greek prefixes are mono for 1, di for 2, tri for 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. You're going to want to know these. So let's try a couple examples. We're given the formula first, and we're going to supply the name, MgSO4.7H2O. So let's focus on the MgSO4 first. The metal is magnesium. SO4 is a polyatomic ion called sulfate. 7, the Greek prefix for that is hepta. And we list the suffix hydrate. So the total name is magnesium sulfate heptahydrate. FeCl3.2H2O. Fe is iron, which we're going to have to indicate the charge on the iron. Cl is chlorine, but that would become chloride in an ionic compound. We can work backwards, starting with the anion, to figure out the charge on our transition metal. So chlorines are anion. Chlorine in a compound forms a -1 charge. We've got 3 of them according to our formula, so 3 -1 charges. For every 1 iron, iron must be a +3. So this would be iron 3 chloride. And then 2 is di, the Greek prefix, dihydrate. Now working backwards, copper 2 sulfate pentahydrate. Copper 2 is Cu2+, sulfate is SO4 2-. So our positive and negatives are going to cancel when we put those together. And then penta is 5. So our formula will be Cu SO4 dot 5 H2O. And the last one, sodium carbonate decahydrate. Sodium is a representative element. It forms a +1 charge, group 1A metal. Carbonate's a polyatomic ion, CO3, and it has a -2 charge. Deca, the Greek prefix deca, means 10. So when we write our neutral formula for sodium carbonate, we're going to cross those charges, 1 after the carbonate, 2 after the sodium. Our formula will be Na2CO3 dot 10H2O. And that's how you name ionic hydrates. Now we're done with all the different types of ionic compounds, and we're going to learn how to name molecular compounds, specifically binary molecular compounds. So we're only going to have 2 different elements together. Writing a name from a formula. When we have molecular compounds, we can combine all of the nonmetals in many different ways, not just one fixed way like with ionic compounds. We have to indicate how many atoms of a particular element there are by using those same Greek prefixes that we used for hydrates. The pattern for naming molecular compounds, we use a prefix and we name the first element. We use another prefix and we name the second element, and we change the ending to "ide." If there's only one of each particular element, the prefix mono is not included on the very first atom. Okay, so let's try some examples of naming molecular compounds. CO, there's an unwritten one after each of those, but we don't have to include the Greek prefix for the carbon because that comes first. So this would be named carbon, and then for the oxygen we'd say monoxide, changing the ending to IDE and adding the prefix mono. We don't write monoxide, so one of the oxygens is dropped. Whereas CO2, now we got to indicate that there's two oxygens in the formula. So this is named carbon dioxide. N2O4 would be dinitrogen. And the prefix for 4 is tetra, but we write tetroxide. Once again, so we don't have an A and an O next to each other. SF6 would be sulfur, and the prefix for 6 is hexa, and then fluoride. N2O would be dinitrogen. Monoxide. Naming molecular compounds and writing their formulas is a lot simpler than with ionic compounds. So working backwards from the name, carbon tetrachloride, so carbon's first, C, and then we need 4 chlorines, Cl subscript 4. Dihydrogen monoxide, so hydrogen, and the di tells us there's 2 of them. And then monoxide means there's 1 oxygen. So that would be the name for water, H2O. Phosphorus pentachloride. Phosphorus, and then penta means 5. So we're going to have PCl5. Nitrogen triiodide. Nitrogen, and then iodine, and then the tri tells us there's 3 of them. Next, we're going to learn the naming rules for acids. Acids are compounds that contain a hydrogen atom. That's how you will identify them. You will see a hydrogen written out front. When it dissolves in water, it breaks up into a hydrogen ion and then some anion or polyatomic anion. So for example, you may have heard of hydrochloric acid. Hydrochloric acid is HCl dissolved into water. And there's no HCl molecules together. Instead, swimming around is a bunch of hydrogen ions that are surrounded by water molecules and chloride anions that are surrounded by water molecules. Writing AQ after a compound means that it's aqueous or dissolved in water. So our aqueous ions are actually what's swimming around in a container that's labeled hydrochloric acid. There is no molecular HCl. It's 100% ionized into the hydrogen ion and the chloride anion. So when we're looking at formulas, how we identify that they're an acid is we look for that hydrogen listed out front. First, we'll name simple binary acids. Binary acids contain 2 different elements, but one of those elements has to be hydrogen. So we're looking for an H out front and then some other anion that it's with. The way that we write a name from a formula is we follow this pattern. The word hydro goes out front as a prefix. We name the anion, but we change the suffix now, not to "ide," but "ic." And then we add the word acid after it. For example, HCl, and I've highlighted all of these acids with the letter H. I've also written AQ out back to indicate that they are, in fact, an acid dissolved in water. If we had HCl, but it did not say AQ, we could not be for sure that this is an acid. It could just be a molecule. And then we would name it with our molecular rules. So this would be hydrogen chloride. But now we're indicating that it's an acid by adding the aqueous after it. So we're going to follow our acid naming rules. We use the prefix hydro. We name the anion, which is chlorine, as chlor. We add the suffix ic, acid. So hydrochloric is actually all one word. Hydrochloric acid. HBr, this would be hydro. We're always going to use that same prefix. Bromine is the anion now, so it would be bromic, and then the word acid. H2S, so this is a binary acid made from sulfur. This would be hydrosulfuric acid. We're always following that same trend, using the prefix hydro and the suffix ic, acid. This can be true for any binary acid. Going backwards, we're still going to write a neutral formula. And how many hydrogens there are in our formula will be dependent upon the charge of the anion. Hydrogen always forms a +1 charge, so however many hydrogens we need to make the formula neutral will be what's listed. Hydrofluoric acid. So fluorine is a group 7A nonmetal and it has a -1 charge. So to write a neutral formula, we would have our H out front, followed by our nonmetal, which is fluorine, and then we list AQ after it. Hydroselenic acid. Selenium is Se, group 6A nonmetal, forms a -2 charge. Now when we write a neutral formula, since hydrogen always forms a +1 charge, if we go back to our old rule of writing the crisscross and put a 1 after the selenium and a 2 after the hydrogen, that'll give us our neutral formula. We'll have H2Se followed by AQ. Hydronitric acid. Nitric comes from nitrogen. Nitrogen is a group 5A nonmetal and it forms a -3 charge. It'll be paired up with hydrogen, which forms a +1 charge. We want to cross our charges, the 1 after the nitrogen, the 3 after the hydrogen. So our neutral formula will be H3N followed by AQ. Remember, the AQ is important to indicate that it's an acid. Oxyacids are compounds that contain hydrogen, oxygen, and then some other element. They're acids that are derived from many of the polyatomic ions we learned. They still release hydrogen ions when they're dissolved in water, and therefore they are still considered acids. A few patterns for writing the names of them will depend upon the name of the polyatomic ion it's derived from. So one pattern might be, we name the polyatomic ion, but we change the suffix to ic acid. Another pattern is we name the polyatomic ion, and we change the suffix to us acid. If you have a polyatomic ion that has the ending ate, that becomes the ending ic. If you have a polyatomic ion that has the name that ends in ite, the name changes to us. So ate becomes ic and ite becomes us when naming oxyacids. In the following example, we're given the formula of an oxyacid and we're asked to supply the name. I highlighted the polyatomic ion portion of the oxyacids. So remember, there's 3 different elements, hydrogen, nitrogen, oxygen in the first one. And we want to indicate what the name of this is. We don't use hydro out front because that was for binary acids. So think about what polyatomic ion is involved in this oxyacid. NO3 minus. The name of that polyatomic ion is nitrate. The ending 8 gets changed to ic in our name. So the name of this acid would be nitric acid. We still add the name acid at the end. Compare that to HNO2. NO2 minus, that polyatomic ion is called nitrite. The ending ite gets changed to us, OUS. So the name of this acid would be nitrous acid. That's the pattern that you follow when naming oxyacids, which is another reason it's important to know your polyatomic ions. H2SO4. SO4 has a -2 charge, and the name of this ion is sulfate. So the ending 8 will get changed to ic, and the name is sulfuric acid. And there's 2 hydrogens in sulfuric acid, notice, because the charge on sulfate is -2, and it still had to be a neutral formula. H2SO3. SO3 also has a -2 charge, and the name of this is sulfite. We're going to take the ite ending and change it to us, and the name of this acid would be sulfurous acid. You can remember the changes by thinking, I ate something icky and I bit something and it was delicious. We're almost done with all of our naming practice. The last thing is to work backwards on our oxyacids, writing a formula from a name. We still have to write our neutral formulas. Remember, hydrogen will always form a +1 charge. You need to know the charges on those polyatomic anions to figure out how many hydrogens you need to write a neutral formula. Let's give these a try. We're given the name and we need to supply the formula. Carbonic acid. Carbonic acid must have came from the polyatomic ion CO3 2-, which is called carbonate. Notice the 8 would have been changed to ic. So when we write the neutral formula, what we needed to know was the charge on that ion was 2-. Since I know that hydrogen in any one of our compounds always forms a +1, that tells me I need 2 hydrogen ions for every 1 carbonate anion. My formula will be H2CO3, and then because it's an acid, I'll put aqueous behind it. Acetic acid is the acid that's formed from the acetate anion. Acetate is C2H3O2-. And since that whole polyatomic ion only has a -1 charge, I only need 1 hydrogen with it in the formula. That will be HC2H3O2, AQ. Phosphorus acid. So notice our ending is OUS. So this didn't come from phosphate. It must have came from phosphite. Phosphite is PO3 3-. So the ite became us. And the number of hydrogens that we'll need in our neutral formula, the charge is 3-. Each hydrogen's +1, so we're going to need H3PO3, and then we list AQ. Perchloric acid. So we have an ending ic. It must have came from a polyatomic ion that ended in 8. Perchlorate is ClO4 minus. And it has a -1 charge, so we're only going to need one hydrogen ion. So HClO4 minus AQ. And another one in the perchlorate family, hypochlorous acid. The ending OUS tells me it must have came from a polyatomic ion that ended in ite, which would be hypochlorite in this case. Hypochlorite is ClO minus. When we write our neutral formula, hypochlorite also has a -1 charge. So we only need one hydrogen. And I noticed there's a negative there that needed to be erased in the last one. HClO-AQ. So we don't want to include any charges in our final answers. And that's how we work backwards from the name to the formula with oxyacids.